Hello and welcome. So, this is our second tutorial of electrical measurements and instruments, and in our last class we have seen the working principle of an ammeter, of a particular type of ammeter which we call permanent magnet moving coil instrument, PMMC, or D'Arsonval galvanometer, and we have found the expression for torque and the deflection angle. So, let us recall them in brief. So, recall that the deflecting torque Td, d for deflecting, it was given by BAN multiplied by I, and this BAN, these are all constants. B constant, flux density constant, area of the coil is constant, number of turn is constant. So, all these constants we can write together as a common constant, and I am giving it a name G. So, we can write that Td is equal to some constant d G multiplied by current, and then this G is often called the galvanometer constant. Now, the name is not that important, but what is the dimension of this G? The dimension of G is torque per unit current. Okay. This is called galvanometer constant. Then we have seen that the controlling torque, which is nothing but the spring torque Tc, is given as k theta. K is the spring constant, and at equilibrium we have Td equals Tc, which implies that BANI is equal to k theta, or we can write that theta is equal to BAN by k multiplied by I. This is equal to some constant times I, and this constant S can be called as displacement constant. Once again, the names are not that important to remember. You need not remember this or memorize these names, it is not required, just need to understand it. Okay. Now, what is S? This is nothing but theta by I. So, S is like theta by I, which is like the deflection or angle per unit current. Okay. This we can also call as the sensitivity of the instrument. Okay. And that is why I have used the letter S. Okay. Why sensitivity? Because if we have an instrument where for smaller amount of current I we get larger amount of deflection, we say that instrument is more sensitive because it can detect or measure smaller current, because we can get higher deflection with smaller amount of current. So, S is a measure of sensitivity, how sensitive that instrument is, that meter is. More the sensitivity is, we can measure smaller current easily. So, this is, we call this sensitivity. This is nothing but the deflection per unit current. So, this is the definition of sensitivity. This you should know. Okay. Now, I would like to mention some small facts about the construction of this instrument, which is a bit more detailed but it is interesting to know. Okay. So, basically I am going to talk about why we have this pole faces curved like a cylinder. Okay. So, this is what we are going to talk about. Why the pole faces are curved, and also why do we have the cylindrical core. So, let us look at these questions briefly. So, these are two pole faces and we have a cylindrical core. Now, the core will definitely increase the amount of flux increase the flux density, because this core has a higher permeability, lower reluctance than air. So, more flux will pass through this north to south pole. So, more flux can now pass like this. Okay. Then if we did not have this core, then the flux density would have been lower. So, the core increases flux density, B. So, if we have higher value of B, which means here if you see the expression for S is B A n by K. So, if B is higher, then sensitivity will be higher, Okay. So, you will have a higher sensitive instrument. Secondly, this core and these curved faces of the poles make the flux lines radial. Radial means so the flux lines are like this. So, they go like radially, or that means these lines are almost perpendicular to this circular or cylindrical surface of the core. If we did not have this core, or if we had say this pole faces flat like this, then the flux lines would have been almost parallel like this. This is generally not used, this is generally used. I mean, this is how it is constructed generally, this is not used. Now, if we have this situation where the poles are flat and we do not have any core, then you see we will have a some small problem. Suppose this is my coil, which is now at this angle. Okay. Now, when it carries any current, it will have some force acting on the two sides, and the direction of the force will always be perpendicular to the direction of the flux lines and the current. So, here this will be the force, and then the torque will be, so the torque will be this force F multiplied by this distance, call it x. Okay. And this is not same as F times d, where d is this distance, the width of the coil. Now, therefore, depending on the position or the angle of the coil, we will have different value or different expression for torque here. Okay. So, in this case the torque expression will be different from this case. Similarly, the angle of deflection will also be different in this case from this. But here you see that if I have the coil here at any angle, the flux lines are always like this. So, this flux lines are radial, which means it is always along the coil, and therefore, the force will be in this direction. And then the perpendicular distance between the two forces is still the diameter d, and this is always d irrespective of the angle of this coil. Here it is not so. So, this is generally not used. This is the situation which we have in our ammeters. Okay. Now, let us move to another topic, another type of instruments which is very similar to this instrument, PMMC instrument, and this new instrument is called Electrodynamic Instrument. So, this is again an ammeter. Okay. Now, let us draw the two instruments, two type of instruments side by side. So, on this side let me draw the instruments that we have just studied, PMMC, and here we will draw electrodynamic. Okay. So, in PMMC instruments what do we have? We have a pair of magnetic poles, okay, it is not normally flat, generally it is like this, and you know that these two sides are actually connected, and we have the coil here, we also have the cord, and the coil turns in this magnetic field. Okay. In electrodynamic instruments, the only difference is that instead of having this permanent magnet, so this is a permanent magnet, here we will use electromagnets. So, here we use electromagnet. Electromagnets are nothing but coils or solenoids. So, we will have a pair of coils So, I will have one coil like this, so these are the turns, these are the different turns of a coil, and this is one end of this coil and this is another end of this coil. Now, here again I will have another coil which again is like this. Okay. So, these are the sides of this coil, and this is one end and this is another end. Now, if we have any current I through this and also some current I through this, so this will act like a let me draw the coil completely for a better visualization. So, now if there is some current, it will generate some magnetic flux like this. This can actually be continuous. Okay. So, you will have many lines of forces, many lines of force, and then we of course have this other coil, which is this one here. This is the coil that moves, that turns. Okay, this is the same coil as this. The only difference is that here we have electromagnet instead of a permanent magnet. Okay. So, this is the only difference. Okay. And now, here we know that T d deflecting torque is equal to B A N times I, where I is the current through this coil. Okay. So, what will be the expression for torque here? So, roughly speaking, so we can say that the flux density B here will be proportional to this current which flows through this pair of coils. So, I can actually join these coils, these two coils together in series. So, that same amount of current flows, and let me call this current as IF, or you can call it I fixed, because these two coils are fixed coils, they do not move, they do not turn, they are stationary, they do not move, but this central coil moves. Like here, this permanent magnet does not move, but this central coil moves. Similarly, here these two electromagnets do not move, but this central coil moves. Okay. So, therefore, we call this as the fixed coil. So, these are called fixed coils. This is fixed coils, and this is called the moving coil. This is also the moving coil. Now, roughly speaking, this flux density B will be proportional to I fixed, or in short, for ease of writing, let me just write IF, F for fixed. Okay. So, B will be roughly proportional to IF. And now, if the current that is flowing through this coil, call this as IM, M for moving. Okay. If this current is IM, then roughly TD is given as it is proportional to B A N times I M, this current, and then this is roughly proportional to as I F A N I M. Now, Okay, A and N, these are constants. So, roughly speaking, we can write this is proportional to IF and IM. Okay. So, where IF is the current through this coil and IM is the current through the moving coil, fixed and moving coil. So, TD is proportional to IF IM. Okay. So, why I am saying this is a rough idea? This is because, just note that in this case we also have the code. The flux lines are radial, and with uniform density, uniform radial density. But in electrodynamic instruments, generally no core is used. Okay. In electrodynamic instruments, normally no core is used. There is no core here. Also, these coils, these fixed coils, they also do not have any core. That is why I have not drawn any core here. I have just drawn a dashed line for ease of drawing, but there is no core. I will tell you later why we do not use any core. But right now you just know that there is no core in electrodynamic instruments. Therefore, it is not possible, it is impossible to shape the flux lines. So, flux lines are not radial, as in this case flux may not be uniform, it is it may be non-uniform, it may be non-radial. So, this expression is not I mean not this expression, this derivation is physically speaking not very precise, but this is true. TD is proportional to IF IM, this is true, but TD is proportional to IF IM is correct, is true. Okay. Although this derivation is not very precise. Okay. Now, we will give you a more precise expression for this deflecting torque. Expression for deflecting torque in an electrodynamic instrument. We will not derive it now, we will first write the expression and understand what it means. We will not derive it in this video. So, the expression is like this: TD is equal to IM IF, it is proportional to the two currents in moving coil and in the fixed coil, and the proportionality constant is this dm d theta. What does it mean? So, here m stands for the mutual inductance between fixed and moving coil, and theta is the angular position of the coil. So, theta can be the angular position of this coil measured with respect to some position, some reference position. Maybe this is my reference position, then this is theta. Okay. So, this is basically the angle theta. Now, what is this mutual inductance? We know that if we have two coils nearby, so this is one coil and say there is another coil which is placed near to this coil, and then if we pass some current in this coil I, so it will generate some flux lines, and some of these flux lines will also intersect or link with the turns of the other coil. Therefore, if this say this current I is changing, if I have say AC current, okay, then this I is changing, and therefore this flux will also be changing, and this flux is linked with the second coil. And so, if I connect a voltmeter here, so this is the symbol of a voltmeter, I will get some reading. Why? Because the current here in the first coil is changing, which is changing the flux in the first coil, which is also linked to the second coil, and therefore some EMF or voltage will be induced. So, I can get some reading here. Therefore, and this is called the mutual inductance. Now, the mutual inductance M or M, this we can define as say the rate of change of current in first coil, and on top we will have the voltage induced in the second coil. This is also same as, I mean, if we had say a current source, a current or a voltage source connected here, and if we measure the voltage across the first coil, so we have a source here and we measure the voltage here. So, this will also generate some flux lines which will link to the first coil, and therefore, we can get some reading here. So, we can also write that this is same as the voltage induced in first coil divided by the rate of change of current in the second coil. This also can be written as, you know that another possible definition is that say flux linkage in one coil, okay, divided by current in the other coil. So, if there is a current in the first coil, what will be the flux linkage in the second coil, or if there is a current in the second coil, what will be the flux linkage in the first coil. So, this is also another way of defining mutual inductance. So, we expect that you are already familiar with this definition. So, this is not a tutorial on mutual inductance, but rather this is a quick recapitulation. But the essential thing that I want to bring out is that M, mutual inductance, depends on the positioning of the two coils. For example, if I have two coils very close to each other, then M is high. But if I have the two coils quite far from each other, then M, the magnitude of M, so the magnitude of M is low in this case, okay, because here more flux can link them together, but here I think very little amount of flux possibly can link them. Okay. So, M depends on the positioning. It also depends on the angle between the two coils. Okay. So, let us consider our electrodynamic instruments, where we have, you recall that we have two pairs of coils. This is say fixed coil, this is one of the fixed coils, this is another fixed coil, and they are carrying some current, they may carry some current IF, and we have a moving coil between these two. So, whose turns are, let me draw it like this. So, the turns of the moving coils are like this. Okay. Now, this coil can rotate. So, this coil can rotate, and therefore, we can have different situations, like this is one situation, we can have another situation where the middle coil or the moving coil is like this, or we can have another situation, say where the moving coil is like this. So, you see that in this case the two sets of coils are aligned, their directions are aligned. So, the flux linkage between this will be very high. So, the flux lines will link them very well. Whereas, in this case flux lines cannot link them that well, because the two coils are perpendicular to each other. So, here we will have high magnitude of M, here we will have a low magnitude of M. So, essentially we see that M depends on the angle between the two coils theta, or the angular position of the moving coil. So, we can write m as a function of theta, right. So, m is a function of theta, and if so, then we can take the derivative d theta of m, okay, and this is what we have in this expression for the deflecting torque. Okay. So, the deflecting torque is proportional to Im If dm d theta, where we have studied what is the meaning of this term dm d theta. Okay. And then, so let me conclude this by discussing the equilibrium condition. So, Td deflecting torque, the torque that tries to deflect or turn the coil, is given as Im If dm d theta. The controlling torque Tc given by the spring is again according to Hooke's law k multiplied by theta, and therefore, at equilibrium these two torques are same. Td will be equal to Tc, which means Im If dm d theta will be same as k theta, which means theta is equal to Im If dm d theta divided by k. Okay. So, the angle of the coil is proportional to the product of the two currents Im If, and these are the proportionality constants. Okay. Now, last thing I will discuss in this video is that, so in this arrangement we have one current through the moving coil, another current through the fixed coil. Okay. So, now what we can do, we can pass a constant amount of current, a known amount of current, and an unknown current Im, and therefore, we can find the unknown current by observing the angle of this coil. But this is not a nice way to do that, because we need another extra current source or voltage source to excite or magnetize this fixed coil. So, a simpler way of using this device, this instrument, is to connect the two sets of coils both in series. So, let this be my fixed coil, and let this be the moving coil. I will connect both in series. So, like this, and I will pass the same current I through both of them. Okay. So, basically I have Im is equal to If is equal to some constant, some current I, and therefore, then we can write this theta as, in place of Im I write If is again I divided by k dm d theta, which is same as I square by k dm d theta. Okay. So, this is how we can use this instrument, by connecting the two sets of coils in series. Thank you. Let us meet in the next video.